Hiya. So in this video, we're going to be talking about tangent spaces. So the idea here is that so last time we talked about coordinate systems and like polar coordinates and Cartesian coordinates. And then we've talked about the difference between affine space and Euclidean space. And so we're going to kind of take these and put them together and try to see what this kind of does. So in essence, what we have is in vector spaces, we can kind of consider all vectors starting at the same point, right? Like everything starts in the same point, so it doesn't matter. But now what we want to do is we want to now be able to take that vector and look at it from the lens of a different point. So we want to look at vectors in different point spaces. And this gives us the idea of what's called a tangent vector. So a tangent vector, VP, to an is a vector v, so we have some vector, which begins at the point P. So beginning at the point P in an. And then we're going to consider the tangent space to be the set of all of these points at this point P of all tangent vectors. So the first thing to kind of note is that the tangent space is a vector space, right? So if we look at a vector space, right? So this is dependent on our P, and it's going to be a vector space in itself, right? Because adding and scaling vectors doesn't change the point itself, right? You only change the point if you act on the point itself with a vector. So adding vectors, multiplying vectors, scaling vectors, whatever, it doesn't really change things. So it is still a vector space. And then since we can add one vector to any other vector, right, in En to a point, then this TP AN is just a copy of En. Now what this is basically saying is that TP AN is isomorphic to En. So no matter what point we pick, there's going to be a vector space around this point, and this is isomorphic to En. And since this is a vector space, we can describe a basis, right? So this is where we're getting a little complicated, right? So at first we just talked about vectors and bases and whatever, but now we're literally going into like, okay, I pick a point, I looked at the vectors around this point, this is going to give me a vector space. We're going to look at a basis for this point, so we can pick a basis for B, and we can choose if we wanted, like if we want to go cray-cray, we can choose a different basis for every single point. For every point, we can choose some different basis. It doesn't even see. And later on, we'll actually see this might be the actual good thing to do. But for now, since we're kind of we want to go slowly, we want to figure shit out. And since we're working with Cartesian coordinates, we're going to fix the basis B for every tangent space. So in other words, notice how we highlight it. We're going to fix this. In other words, B, our orthonormal basis, will be the basis for every tangent point. So B is equal to BP for every P in AN. And this will allow us to continue to write the vectors as column vectors with square brackets, etc., as we did in the end. So nothing is really changing. But it could change, and this is the things to kind of be a little hesitant on. Now the name tangent vector, so a little remark, the name tangent vector and tangent space, they it might seem weird. You're like, well, we're tangent, if we're considering normally it's some line that's tangent to some curve. Where's this tangent? Nothing is tangential here. Where is this coming from? This we'll talk about many weeks in the future. Well, I don't know how many weeks in the future, and it'll be a little more clear hopefully by then, so don't worry about it for now. And also another thing to remark is when we're doing vector calculus in R3, you'll probably have noticed this notation where we have I, J, K as our notation, and here the I, J, Ks are the tangent vectors. Or no, sorry, the AI plus BJ plus CK are the tangent vectors. And this basically gives us a vector of the tangent space without knowing the point at which the vector begins, since it doesn't really make sense on its own. So like just a quick little notational thing. This by itself doesn't really tell us too much, but it does tell us some things. We're gonna end this video on one last definition. And then since this is a lot, it's a big thing, these tangent spaces, like conceptually, we also went over affine spaces. It's a lot of new info. We're gonna stop after this one. So like if there's any questions, really ask them, because we're gonna keep going into these further into detail later on. So you really need to know these. So we're gonna make a quick note on functions on affine space. So like, remember we talked about linear operators. The idea in affine space is that we have functions. And we're eventually going to do differential geometry. That's the name of the section. So we want our functions to be differentiable. So what we want, so hopefully y'all remember your calculus. And basically what we're going to do is define a smooth function. So if you don't remember your calculus, come talk with me. Now's the time. You will have problems in the future if you do not get this down. So ask now, double check. So what we're going to do is we're going to say a function. So f is a real valued function on an. So we go from some vector or some point x1 to xn to f of x1 to xn. We're going to say f is smooth if every partial derivative of x exists. So let's see how well you remember the partial definition, the partial derivative notation. This should be, if this writes, dn of f divided by x1a1, right? Because we want every partial derivative. So I should be able to take every single one, a of them, x2a2 all the way to xnan. And here the conditions are that the summation of the points have to be equal to a. I think I should have I wrote this wrong. This should be a on top. There we go. That makes more sense. I was like, something's off here with notation. So for now, don't worry about too much about this definition, but you should start remembering derivatives and something like this. So don't worry about it too much. For us, what it basically means to be free, to be smooth, is that we can keep taking derivatives without any problem. So no matter how we take our derivatives, we're good to go. So this is like the main thing we want to worry about. Most of the functions we will work in the last half of the course will be smooth functions, so don't worry too much. But yeah, so we will end this video here. Again, this was a shorter week because it's some heavy topics. As always, if you have questions, make sure to ask, because we want you all passing and succeeding in this class. So yeah, so I will see you in the review sessions. So yeah, have fun. See you next week.